Right here you see the definition of a vector space. So you have it here to refer to right at the beginning of the video. When you want to look back at it, you can. Let's consider a set here. So we're going to look in this video at this one set, a set of 2x2 matrices of this form, where you have in the first row, first column position, you have a real number. In the second row, second column, you have the same real number, and zeros everywhere else. So I'm going to call this set V, is the set of matrices that look like this. So this is set notation. So this says V is the set containing these 2x2 matrices that I've described, where you have A, 0, 0, A, where A is a real number. This set V is a vector space. How do we know it's a vector space? Well, because that set satisfies the 10 axioms that make up the definition of a vector space. So we're going to have to get kind of mathy here and talk about things in a mathematical sort of a way. Not exactly, we're not going to exactly prove things, but we're going to be headed in that direction. So there are 10 axioms. We know this because V satisfies 10 axioms. And that's a lot. That's a lot to show. So let's talk about some of the elements of this set, or this vector space V. So let me just give you a few examples of matrices. So like 5, 0, 0, 5, that's in V. And -2, 0, 0, -2, and pi, 0, 0, pi. And also 0, 0, 0, 0, that's also in there because these two are real numbers and they match, and these two are zeros, etc. So these are all matrices that are in that set V. Now because we're calling V a vector space, we're going to call the elements of that set vectors. So the term vector is now going to encompass a much larger, more flexible bunch of things. In this case, because the set that is a vector space contains matrices, we're calling these matrices vectors. And we can call vectors vectors, we can call matrices vectors, we can call, and will call, polynomials vectors. Any set that contains elements that satisfy the 10 axioms that you briefly looked at the beginning of the video is a vector space. So let's start going through the axioms. So I'm going to write again, V is equal to the set containing things that look like this, where A is a real number. So I'm going to put a few general vectors in there. So I'm going to call the vector U x, 0, 0, x, where x is some real number. I'm going to call the vector V, because we're going to need these for the 10 axioms to show that this is a vector space. I'm going to call Vy 0, 0, y, and we're going to need a W also, so I'll define a W as Z, 0, 0, Z. So I'm distinguishing between a vector, just the way we have been since we introduced vectors a while back in class, where you have a vector is indicated with an overbar. Some books will use a bold also. So this U and V and W, they're vectors because they have overbars, whereas X and Y and Z are just real numbers. So the first axiom, in order to be a vector space, the set must be closed under vector addition. And I'm using the word vector again to be general. In this case, the vectors are matrices. So we've got to convince ourselves that V is closed under this vector addition, which would be matrix addition. So what does that mean? That means if you take two elements from that set and add them together, you get another element in the set. So you can't bump yourself out of the set by doing the vector addition. So if we look back at these examples of vectors that are in that set, if you add any two of these things together, like if you add these two guys together, you're going to get 3, 0, 0, 3. That's in V. If you added these two together, you get pi minus 2, 0, pi minus 0, pi minus 2, and so on. So you add any of those any two of those vectors together, you get another vector in the set. That's what it means to be closed, is under some operation, is that the operation can't bump you out of the set. So, but I just convinced myself with particular examples, we want to show in general that this is true. You need to show that U plus V, when you're talking about a general vectors in that vector space, that this gets you something that's still inside of V. So I'm going to actually do this out. So U, the vector U, is the matrix x, 0, 0, x, and the matrix V is y, 0, 0, y. So you'd get x plus y, 0, 0, x plus y. Is this still in V? The answer is yes, because x is a real number, y is a real number, so x plus y is a real number. So you have the same real number along the diagonal here and zeros everywhere else. So V is closed under addition. That first axiom is checked. The next, pardon me, the next axiom is that addition is, what's the word for it when you can change the order? I think it's commutative. I hope so. I think it's commutative. So if you take U plus V, that's got to be the same thing as taking V plus U. And this is going to be true in this case. This is going to get inherited from properties of real numbers, because if you do U plus V, we did U plus V up here, we get x plus y, 0, 0, x plus y. And of course, the real numbers addition is commutative, so you can change the x plus y to y plus x, 0, 0, y plus x. And so this is y, 0, 0, y plus x, 0, 0, x, which is V, vector V plus vector U. And so U plus V is equal to V plus U. The addition is commutative. That second axiom is satisfied. So that one's good. Next is the addition is, I think it's associative is the word. I've never been good at remembering these words. Anyway, if you do U plus V and then you add another vector W, that would be the same thing as doing the V plus W first and then adding the W, so you can scooch these parentheses from here over to there. And so again, this is going to get inherited from properties of real numbers. So yeah, I guess I'll do it out. So we have U plus V again up here was x plus y, 0, 0, x plus y. And then if you add the W I defined up here as z, 0, 0, z. And so when I add these guys together, I'm going to get the x plus y plus the z, 0, 0, and then x plus y plus the z here. And then, because of the associativity of addition in real numbers, I can scooch these parentheses from there to there. X plus y plus z, 0, 0, and x plus y plus z. And so, I guess I'll come down a little bit here. So this is x, 0, 0, x plus y plus z, 0, 0, y plus z, which is x, 0, 0, x plus y, 0, 0, y plus z, 0, 0, z. And so this associativity gets inherited from the real numbers. So the third axiom is satisfied. Fourth. What has to happen fourth? I'm going to cover this up so I can keep using my vector space here and use this definition. So the fourth axiom is V must contain a zero vector. or what you might call an additive identity. Which we're going to call the zero vector, even though depending on how your vector space and its operations are defined, might not actually be a zero. In this case, it really is a zero vector, or a zero matrix. Because an additive identity just needs to be something that no matter what you add it to in the vector space, you get that thing back again. So we have to have 0 plus u, any general vector in the vector space, give us back this u. So 0 plus u has to be equal to u. And so if we take the 0 vector plus u, you get 0 plus x is x, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus x is x, which is u. So we have an additive identity right there in the vector space, something that I can add to any vector in the vector space and get that same vector back again. So the fourth axiom is satisfied. Fifth axiom, V must contain an additive inverse for all of its elements. I should have said vectors probably. So every vector in V has to have an additive inverse. So we have this additive identity. The additive inverse is going to be something you can add to any vector in V and get the zero vector out. So negative u, which would be the additive inverse of u, is going to be just what you'd expect it to be. Negative x, 0, 0, negative x. Because if you take negative u plus u, you'll get the zero vector, and we can verify that. The negative u is negative x, 0, 0, negative x, plus u is x, 0, 0, x. So when you add those two together, you get negative x plus x, 0, 0, negative x plus x, which is our additive identity. And so every vector in there, everything that looks like this, real number here, same real number there, 0, 0, you take the negative of whatever that number is. So if it's 5 and 5, the additive inverse would be negative 5, 0, 0, and if it was negative 3, it would be 3, 3, 0, 0, and so on. So every vector in there has an additive inverse, and we've checked that, so that's good. Then, when you get to axiom 6, we're starting to get into the scalar multiplication axioms. So scalar multiplication, if you remember from earlier in the semester, when you multiply a vector times a scalar, you're multiplying a vector times a real number. So V must first of all be closed under scalar multiplication. So that is, and scalars in vector spaces, in our vector spaces, are always going to be real numbers. So for any real number k, k times u is still in V. So this is another closure axiom. So it has to be the case that scalar multiplication does not and cannot bump you out of V. And so we take a real number k and multiply it by u. That's going to be k times x, 0, 0, x, which is going to be kx, 0, 0, kx. My k's and my x's, I just realized, look a lot alike. So this is a kx, and this is a kx, and this is a real number, and this is a real number, and they're both the same. So this is inside of V, and we're all good here with the sixth axiom. So this set is closed under scalar multiplication. And then we have a few more axioms about scalar multiplication. So the seventh axiom is that scalar multiplication distributes over vector addition. So it's a distributive property. There are a couple of distributive properties here. So if I have the scalar and I want to multiply it by a sum of two vectors, I should be able to distribute this k through here. So we can't assume that we can, we have to check that we can by using the scalar multiplication and the vector addition that's appropriate for our vector space here. And so the addition is the matrix addition, and the scalar multiplication is just a regular scalar multiplication. So we get k times u plus v. We already did u plus v, so I'm going to sort of cheat a little bit and not write down u and then v and then do the addition. This was x plus y, 0, 0, x plus y. And then I guess I don't know, I don't have my eraser here. I don't need that set of parentheses because I have the matrix. Okay, and then when I do the scalar multiplication, I get k times x plus y, 0, 0, k times x plus y. And so here again, this property is going to get inherited by the properties of real numbers, because now I'm dealing with real numbers. I can distribute the k here and here. I get kx plus ky, 0, 0, kx plus ky. And so I can rewrite this as kx, 0, 0, kx plus ky, 0, 0, ky. And then this is k times x, 0, 0, x plus k times y, 0, 0, y, which is k times u plus k times v. And so if you look at the very beginning of this series of equal signs and the very end, we have shown that the distributive law works here, that this scalar multiplication does distribute over the vector addition. So that one's good. So we've got 7 axioms shown to work here. So we have 3 more. Let me get this set up. So that was 7. Axiom 8. Was I circling them? Yes. So axiom 8 is another distributive law. I'm not sure how to say this one. It's a scalar multiplication distributes over scalar addition. That sounds funny, and I'm not sure I'm saying it right. I'm not too sure about the wording there. But basically here, if you have 2 scalars, k plus l, so we say k and l are real. If we have k plus l, so 2 scalars, and you add those 2 scalars together and then multiply by the vector, that should be the same thing as multiplying k times u plus the l times u. And so the previous axiom, we had 2 vectors that were added together multiplied by 1 scalar. Here we have 2 scalars added together multiplying by 1 vector. So it's a similar but different situation. So I have the k plus l, and I want to multiply by u, which was x, 0, 0, x. Which is going to be k plus l times x, 0, 0, k plus l times x. And then again here, the distributive law of real numbers is going to kick in here, and this property will, for this vector space, will get inherited from the same property of real numbers, because I can distribute this x here and get kx plus lx, 0, 0, kx plus lx, which is kx, 0, 0, kx plus lx, 0, 0, lx, which is k times x, 0, 0, x plus l times x, 0, 0, x, which is k times u plus l times u. And so again, if you look at the beginning and the end here, we have that distributive law holding, and so this one's checked. And then axiom 9 is, I'm not going to try to say it in words. If you have a scalar times a scalar multiple of a vector again, that you can do the scalar multiplication times the vector and then do the next scalar multiplication, or you can multiply the two scalars together and then multiply by the vector. So I'm going to do this out again. So I'm going to get L times x 0, 0, x, which is k times Lx 0, 0, Lx, which is k times Lx 0, 0, k times Lx. And then again, just because I'm dealing with real numbers, I can scooch these parentheses because this is just a real number times a real number times a real number. So instead of doing L times x and then multiplying by k, I can do k times L and then multiply by x. And same thing here. And so this is KL times x 0, 0, x, which is KL times u. And so this and this are the same. And so those are the end products, the result that you need to satisfy this axiom. And then the very last axiom, 10, finally, is that 1 times u is equal to u. And so that's, in this case, scalar multiplication. You just multiply every entry times the 1 and you just get x 0, 0, x. So in this case, this last axiom is sort of trivially true. So 1 times u has to be equal to u. And that's all 10 axioms. And so that works out. And we've shown that this is a vector space. Okay. Very good.